everybody. My name's Elizabeth, and I'm a product marketer at Up42, as well as a geospatial analyst, and I'm your host for today's webinar. Thanks for tuning in from across the globe. Before we get started, I'd like to show you around this webinar platform we're using today, and then go over the agenda. On the right-hand side of your window, you'll see the Questions tab, where you can ask us questions, see what others are asking, and upvote questions that you'd like to answer. During the transitions between speakers, we'll also have topical polls that you can answer under the Polls tab. You can also interact with us and each other in the chat. If you're watching this live, our speakers will answer your questions after their presentation and at the end of the webinar as a part of our roundtable. So that means feel free to ask your questions even as the presentation is in progress, so it can get upvoted and your question will be more likely to be answered. So with that sorted, welcome everyone to Up42's first infrastructure webinar, where we will discuss with some great minds from across the industry how remote sensing may or may not be a replacement for ground-based monitoring of critical infrastructure. First, we'll begin with an overview of the speakers joining us today and their respective companies, followed by a demo of the Up42 platform for an infrastructure monitoring use case. Today, we'll have guest speakers from renowned companies in the geospatial tech industry. If you're not already familiar with these companies, allow me to introduce them to you. First, there's AI Dash. AI Dash is an AI-first SaaS company enabling satellite-powered maintenance for utility, energy, and other core industries. Then we have Intermap, a company with 24 years of leadership in the geospatial industry. You may know them from their proprietary NextMap database to their analytics and solutions. And finally, we have Catalyst, a PCI geomatics brand that provides cutting-edge algorithms rooted in photogrammetry and remote sensing. Thank you all for joining us. Now that we're all anticipating today's presentations, allow me to invite Up42's very own Thais Ben-Dixon to the virtual stage for a demonstration of Up42. As Thais is coming on the stage, let's get to know a little bit about our audience today, checking out the Polls tab for our first polls question. Let's kick it off with a simple one. What industry are you all working in? Feel free to answer in the polls. Thais is a data science engineer at Up42. She earned her master's in geosciences at the University of Potsdam. And over the past 5 years, she's worked with all types of geospatial applications, from climate studies to smart city planning. Thais, thank you for being here, and the virtual stage is all yours.
Thank you for the introduction, Lizzie, and hi, everyone. I'm just gonna share my screen. One moment. Okay, here we go. So as Lizzie already mentioned, I'm Thais. My background is in geosciences, so I'm super passionate about finding synergies between geospatial data and global challenges. But today, though, I would like to show how Up42 can help you to find solutions to your own business challenges. But before we go there, of course, we should talk about what Up42 is and what we're doing at Up42. So Up42 is a developer platform and marketplace to derive insights from geospatial data at scale, meaning we want to enable developers to build solutions based on geospatial data and analytics. We do this by offering data from satellite and aerial data providers with off-the-shelf analytics in an easy-to-use platform. For those of you that just want to use geospatial data, you can access all available datasets via a single Up42 API. So why should you be using Up42? Well, there are 3 key problems in the geospatial industry that Up42 addresses. The first one being that geospatial data is fragmented and spread across multiple provider platforms, and it's often also very hard to build and distribute algorithms, specifically or especially if you want to do this at scale. So what is Up42 doing about this? Well, as I already mentioned, we provide an open marketplace for geospatial data and algorithms, meaning we offer 50 data sources ranging from high-resolution satellite imagery and global weather data to elevation data and aerial imagery. We also have 75 plus geospatial algorithms to extract meaningful information for various use cases such as flood mapping, object detection, or vegetation health monitoring. We also have a simple pay-per-use pricing model and enable users to do satellite tasking or ordering of archived images. Up42 also provides a workflow engine and scalable infrastructure, which means we enable you to bring your own data and algorithms into our platform as custom blocks. We do this while providing scalable cloud infrastructure and ensuring data to algorithm compatibility. If you started using our UI today, you would see that it's super easy to use and very intuitive. You can use it to discover and access data. It's perfect for that. And you can also build processing pipelines and run machine learning algorithms without having to write any code, which is really nice. Once you are ready to take the next step, Up42 also has a very powerful API or an open source Python SDK, which not only allows scaling, but also easy integration of Up42 into your own applications. Later in the demo, I'm actually going to give you a bit of a sneak peek on how to use the SDK, and you will see how easy it is to use. But now that you have an understanding of what we do at Up42 and what the benefits are, I actually want to go into a specific use case. So let's imagine a scenario where you are a railway operator, and of course it is in your interest to have secure and uninterrupted transport. Hence, you need effective monitoring and maintenance of your railway networks. And Up42 provides several solutions and data that can help you achieve this. One of the first things that you could do, for example, is look at synthetic aperture radar data, such as, for example, Sentinel-1 or TerraSAR-X data, both available in our platform, and use these to monitor ground movement using, for example, PSI methods. Another thing that might be relevant as a railway operator is vegetation, more specifically trees growing next to the train tracks. And this is important because if trees reach a certain height, they might topple over onto the train tracks, and of course they could damage the infrastructure. And you have a few options to derive tree height. One of the things that you could do, for example, is look at digital elevation models, again, also available in our platform. And you could derive the tree height by subtracting digital terrain models from digital surface models. If you want to be even quicker and more efficient, Up42 has a block that was developed by SpaceBT, which directly is able to determine tree height. And how you would use this block is you would combine it with high-resolution satellite imagery, for example, Spotter Pleiades. On top of that, you would use raster tiling, and then you could add the tree height detection block. And this is actually the workflow that I'm going to show you in the demonstration, and I'm going to use this workflow with the SDK. So if you wanted to start using the SDK, the first thing that you need to do is install the Up42 pipe package. And we have a documentation that is very nice, where you have everything very clearly explained here. I'm not going to go too much into it. You can explore the documentation yourself. We also have some examples on how to run workflows with the SDK, but I really invite you to look at it yourself. Then, of course, we need to import all the necessary libraries. Here I have a few libraries that are not necessarily mandatory, but I want to do a nice visualization in the end, so that's why I have them here. Then, once you're ready to start, the first thing that you need to do with the SDK is authenticate, and you can find your credentials in your project settings. Mine are hidden here, but you could also add them explicitly here in this alternative method. As you can see, my authentication was successful, very nice. And now next, I need to initialize a project and create a workflow. And the project basically contains several workflows, and the workflows are the actual processing pipeline where I would have my blocks. In this case, I'm calling my workflow tree height workflow, since I'm detecting tree heights. And I'm using an existing workflow because I've run this before. Then, of course, I need to select my blocks. And in this case, I already know which blocks I want to use. I want to use the Pleiades data, I want to use the tiling block, and I want to use the tree height detection block, which you can see here. If you're not sure which blocks you want to use, then you can use this method highlighted there to print all available blocks at Up42. So yeah, I add these tasks or blocks to my workflow class, I run this cell, and then I need to start adding parameters. And this is important to check the parameters, because depending on the blocks that you're using or the workflow that you're running, the parameters might change. So I'm getting the information on which parameters my blocks require, and I get the information here. I see for each block, there's a few parameters that can be used. I have the geometry, I have the limit, which is the number of images that I want to have. I have a maximum cloud coverage, and you see some of these parameters have defaults, so not all of them are required. As you can see here with the tiling, this parameter is not required. What's important to check is if the tree height detection block requires any parameters, and as you can see, it doesn't. So very straightforward. Then I can start constructing my workflow and adding the parameters. And the most important thing that you need to add, of course, is the AOI, the area of interest. In this case, I already have an AOI prepared in a GeoJSON file. It could also be a shape file, for example. Or if you want, you could also draw an AOI in your Jupyter notebook with this command right there. So then I add my input parameters to my workflow class right here. I first add my area of interest. I also have, so here's the area of interest. Then I add my geometry operation. In this case, I'm using contains, my time range, and the limit, which the default was 1, but I'm explicitly adding it here anyway. Then what's really important, I want to update my maximum cloud coverage. So if you remember, the default was 100, but I actually want a less cloudy image, so I'm updating that to 10. I'm running the cells, and now I'd be ready to run the job, but before I commit to doing anything or buying data, I of course want to know the price of this workflow. So I'm estimating how much it would cost with this method right here, and it only takes a few seconds, and I will know how many credits this workflow would cost. So it says 1,400, 1,800 to 1,800, sounds very reasonable. Now I'm ready to run my job, and before I run my actual job, I have this dry run. And what it does, it first of all checks if my input parameters are set correctly, and it checks if there's imagery available. If everything is correct, then the job will be successful. If maybe there's no imagery available for my time range or my area of interest, it will fail, or it will tell me I need to correct my input parameters. But here it was successful, so everything is looking good. And now I could run the actual job and get my results. I've already run the cell before, and I already have the results, so I'm not running it here. But usually you would get an output folder, as you can see here. And I'm going to show you how the output directory looks like. So if I go into the output directory, I see several files, and this is because I'm using tiling. And tiling is basically dividing the input imagery to several pieces, and that's why the results are also divided into several pieces. But if you look into it, you can find it right away there, a shape file with the height information of the trees. I could visualize this in QGIS right away if I wanted to. But what I actually want to do is highlight how you can integrate the SDK into your Python code. So I'm going to stay within this Jupyter notebook. And I'm actually going to look at this data.json file, because there I also have all the tree height features compressed into this one file. As you can see there, there's the height. So I copied the path to this file, and I'm adding it to my notebook here. So there's the path to my data.json. And then I have this function cleaning under dash data that I created that is basically just organizing the data and filtering a bit through the data. The notebook will be shared later on, so you can look into it if you're interested. But what it basically does, it creates 2 geodata frames, one containing all the heights of the trees, and one containing only the trees that are above 6 meters, which, I mean, which are the ones that I assume could become dangerous for the train lines. Then I'm using this super cool tool called Kepler GL, which is perfect for visualizing vector data. And I'm initializing the space map, and I'm going to use it to visualize all my geodata frames. Additionally, I'm loading this shape file, which contains a train line in northern Spain, where I'm going to make my risk assessment. So I have all my geodata frames, one with the higher trees, one with all the trees, and one with a train line. And I'm adding them to my Kepler base map, and then I'm going to visualize it. And as you can see here in the plugin, you can already see some of the data. You could, directly in the plugin, make some changes and explore it, change the base map if you wanted to. But I actually already prepared a configuration where you can see everything in 3D. So I'm just going to add that. And as you can see here, we have the train line in purple that I added. And then we have the trees in green with, I mean, not the trees, but the height information of the trees in green. And then the trees that are above 6 meters, they're in red. And already there next to the train line, I can see there's a few trees that are very tall, and they might need to be cut down, if I'm making a very personal risk assessment. But yeah, so this was the demo. I hope it was fun and interesting. If you have any questions, please reach out in the chat. I'll be answering questions there. And I hope you feel confident that Up42 can help you find solutions to your own infrastructure problems that you have. And yeah, I guess that's it.
Thank you, Thais, for that really informative demo that contextualized how our audience can leverage Up42 for infrastructure monitoring and vegetation management. It was really dynamic, so thank you for that. So with that, we're ready to invite the first special guest speakers for today's webinar, Rahul Saxena and Nitin Das. As they join the stage, check out the poll tab for our second question. Thais just showcased the value of Up42, and we'd love to know how many of our attendees have previous experience or exposure to the Up42 platform. So feel free to answer in the polls tab. Rahul is the CTO and co-founder of AI Dash, and as such, he leads the operations and works closely with the product and engineering teams. An IIT Delhi alumnus and serial entrepreneur, Rahul brings with him deep domain expertise in technology, product development, and engineering. He's passionate about AI and machine learning and is keen on problem solving and maximizing efficiency through tech innovations. Joining Rahul is Nitin. Nitin is an AI ML guru and former lead AI scientist at Target, now serving as AI Dash's Chief AI Officer and co-founder. His expertise in deep learning, neural networks, and data science is truly remarkable. Nitin is leading the product development teams, and his goal is to ensure that the company has the right AI solutions and tools to deliver great value to their customers. So with that, the stage is yours, gentlemen. I leave it to you.
Thank you. Yeah, hi, thank you. So hi, everyone. So Nitin and me would be taking the session around satellite analytics and how they are transforming vegetation management for utilities. Hope my screen is visible. Okay. So I'll start with the current state of vegetation management today with most of the power utility companies. So as of today, the process of vegetation management, which is primarily around vegetation which grows around the power lines, the power utilities. So how do you manage trees which are getting close to the wire, both from horizontal and vertical angles? So current process has been mostly manual, not really very data intensive, and not using the right kind of technology, primarily due to absence of availability of right data. So in absence of that, most utility companies go with this concept around cycle trims, where they make some estimates around if you cut a tree today, then when the next tree should be cut, and come with some cycle trim years, which is more manual and an absence of any data. There are no insight available because of lack of this data, and thereby making the whole process quite costly in nature. So as mentioned, as a statistic here, many utility companies spend in excess of $100 million, specifically large utilities, just for this vegetation management piece. At the same time, it's quite important. Its business impact of vegetation management continues to grow exponentially. Specifically from North America, there is a large amount of overhead transmission and distribution lines. Distribution lines go above $6.5 million line miles. 80 to 90% of funding of utility goes in managing these. At the same time, there are other kind of risks which are increasing day by day. So there is this risk around wildfires, which has really grown quite a lot in last decade or so. In 2017 and 18, one of the large power utility in California, PG&E, was facing $30 billion in liabilities, pushing it to brink of bankruptcy. And there are statistics which say if you are able to do the tree trimming in the right way, you can reduce the risk to a large extent. So given this problem statement, so I guess the question then is, where does something like a satellite imagery come into picture? So let me just start with some background there. So satellite imagery, if you look at the history over last 50 years or so, it has really evolved. So what you see on the left side is a 80-meter pixel image, and the same pixel, if you see in the 30 centimeters on the right side, you can see the kind of clarity which we have reached to over these years. So with all this kind of imagery available, having the right kind of AI models, you can now predict and derive meaning out of these images very well. And this is what has happened over the last 50 years, and all this historical data is available. At the same time, if you look at it, this space continues to evolve. So for the decade from 2009 to 2018, there were around 2,000 satellites launched. And from the subsequent decade, almost 5 times that number of satellites would be launched, and of all kind of resolutions. Recently, there was a company which got funded, which is launching a 10-centimeter resolution satellite. So getting very close there, and because of that, it's now possible to measure both horizontal and vertical clearances. So given the context around vegetation management, given what satellites can do today from remote monitoring perspective, so let's deep dive a bit into what AI Dash as a platform does, right? So what AI Dash does is it takes this high resolution multispectral satellite imagery, combines it with the enterprise data coming from electric utilities, whatever is relevant for vegetation management use case. It can be, let's say, data around past outages, the kind of geometry you care about, what are the typical kind of parameters around customer count. So anything which might be relevant for people to make decisions. So all that information is combined with satellite imagery. And then we have a bunch of AI models which enable use cases. From satellite imagery perspective, we heavily rely on UP42 because of their ease of providing data in an API way, in a programmatic way. So we have APIs to get the data, assess which data is available for what areas. You can do tasking. You can get areas, any of this data on a API call. So it's quite useful and been really useful for some of the use cases we are attacking. So given all this data availability, we have written a pipeline which enables these different models. So we are able to predict things like encroachment, prioritization, change detection over the last couple of years, digital elevation models. So there are these different AI models which are now enabled with this imagery. So once all that is done, what our platform does is it helps you plan what do you want to do from task perspective. Given whatever configuration you do there, you can create the tasks, you can prioritize them based on your different business logic, you can assign it to different users, and then you can complete and then even review and audit as well. So we have a set of mobile and web applications which enable all this, and we have a couple of case studies which are available on our website, where based on this workflow we have been able to improve the system reliability by 15%, whereas we're at the same time reducing the O&M cost by 20%. So there are modules which enable wildfires mitigation. We have proven reduction of power outages. There are use cases around disaster management and better control and compliance as well. So essentially, what you get is a 360-degree view of your entire network. We do a bit of data correction as well, whatever shape files we get from the shape file or whatever format we get from the customers. We do a bit of semi-automated correction using satellite imagery. We do the detection around horizontal and vertical clearances at scale. Satellite imagery enables that. We can also detect hazard trees where the health is declining or there's a potential for failure. And with this availability of historical satellite imagery, you can calculate the growth rate and do future predictions. So essentially, given all this, so we come with these different modules which are useful from a vegetation management perspective. So first module is around line clearance, which is primarily around the horizontal and vertical clearances and helping utility companies plan for their cycle trims efficiently. You can also look at, based on the use case and based on the requirements, you can look at going for a mid-cycle trim. There are ways you can do automated post-trim audit as well. This is one of the primary use cases. Then there are a module around hazard tree, and which we have found is very relevant for power utilities. Many of the outages we have seen come not necessarily only by vegetation which is growing along the wire or which is inside the ROW, but many of the trees which are hazard trees can fall on the wires and cause damage. So we have modules which enable detection of those areas as well. There's a module around remote inspection, which can be used for both distribution and transmission lines. So once all this analysis is done through these modules, there is a capability to manage the work for contractors or in-house operators, whoever is working on these. You can assign work orders, you can prioritize, you can schedule, and you can also look at how to manage your budget at quarterly or whatever frequency you want to do it. And then there are a couple of other modules around herbicides, growth regulators, and disruptions management. So from benefit side, like I mentioned earlier, so we have a use case where we were able to improve the reliability by 15%, and the budget at the same time got reduced by 20%. We have ability to provide this solution in a capitalized format. It's just we have both SaaS and perpetual license options, and the solution can be deployed on cloud or on-premise based on your requirements. So just a very high-level view around cycle trim and line clearance. So what these modules do. So one I mentioned was around cycle trim and line clearance. So this module enables you to do the planning around your network years in advance. There are ways you can do cycle time analysis at a feeder circuit or even at span level. You can create plans based on your different kind of business rules and goals. You can execute management, like I said, at circuit, segment, or even span levels. You can do management of hazard trees, and then there are modules for herbicide and work planning. So let me just hand over the stage to Nitin to cover some of the details around these models.
Thanks, Rahul. So this is basically the 3D visualization or the 3D walk of one of the digital elevation model. So as you can see, we can, as Rahul mentioned earlier, using this model, we are able to detect the position of the hazard trees, which are very near to the power line in terms of vertical as well as horizontal clearance, or as well as if the tree is about to fall, or it will basically get tender in next few months. So using this model, the digital elevation model, and our own basically deep learning proprietary model, we are able to detect all these and distinguish the power lines, segment each of the power lines into multiple segments based upon their severity. So yeah, this is the overall thing in this, how we are using DEM as well as our own deep learning models for that. So only you can move to the other slide.
Yeah.
Yeah, so as I mentioned earlier, we are using satellite data, and basically we are using them to identify danger trees. Danger trees in terms of the horizontal and vertical distances from the wire, or the clearance from the wire, and using the state of health of the vegetation, we can very well identify when the tree is about to get tender, and when it will get fall onto the wire if some extreme events happen in the future.
Sure, and this case study is also available on TND World. So I guess, yeah, I mean, that was a brief overview of how we are solving this. So happy to answer any questions here.
Yes, we had plenty of questions that poured in. One thing that personally I'm wondering, when you mentioned that the model, the framework that you guys work under also helps with disaster mitigation, how does that enhance the image for these utility companies, especially in regards to increasing wildfires that we've been seeing recently?
So, sorry, I didn't exactly follow the question. So, how you mentioned around how the image is enhanced, as in
their business image. So, how does your insights that you draw help build a better reputation for these businesses in regards to disaster mitigation?
Right. So, see, the thing is, specifically with respect to wildfire mitigation, and that's the kind of case study and POC we did with Avista as well. So, what we do is we are enabled to figure out which areas are more prone to wildfire, which kind of trees are more prone there. And once those are detected, and based on the business logic from those customers, they're able to plan those things better. In terms of images, like I mentioned, the satellite imagery, the biggest advantage is you can get archive images for last couple of years and do better prediction there and see the change detection over there as well. Nathan, you want to add anything there?
Yeah, basically, as I just wanted to add, basically using satellite image, we can extract multiple attributes like the fuel load, as well as we are also fusing enterprise data like the outages, what kind of outages happened in the past, and fusing all those things together, we can come up with a wildfire criticality score, which basically help the client to better assess the area and plan accordingly.
So we have another question, essentially about the DSMs that you use. They want to know how current do these DSMs need to be, or in regards to like what ortho imagery that you're using to derive your insights.
So definitely. So basically, we require. In order to basically get the current snapshot of the system, we require a latest DSM. For this, we basically capture or we order for the stereo tasking images and use those tasking images to create a DEM.
And we have another one about horizontal and vertical accuracy. So how do you handle reporting this to clients? Maybe if you can share some insights on whether you can tell if there's consistent vertical or horizontal accuracy, and how you do your sort of co-registration process.
Yeah, so basically, so we have a ground validation. So as Rahul mentioned earlier, so we have automated as well as a ground validation. There's a semi-automated process. So we predict and we basically validate from the ground. And then basically, if there's a discrepancy, if there's an error, we basically, that is a feedback to the system, and the system adjusts itself in terms of horizontal and vertical accuracies.
And just to add, so when we typically work with a customer, normally we start with a pilot where we work with customer and go with them for field validation. So as Nitin mentioned, any feedback we capture which is going against our models, those models are readjusted based on that.
Okay, great, thank you. One last question again from our side. How do you incorporate the digital elevation models? You started to touch on this with the DSMs, but can you also use photogrammetry, or have you even found that in some cases it's better to use LiDAR?
So the digital elevation model we have used, a digital elevation model, and we use the digital elevation model by basically using those ortho imagery. So we have used those two kinds of digital elevation model. So we haven't explored by the LiDAR imagery. Obviously, that is more accurate, but the scale at which we work, the LiDAR imagery won't be possible at that scale. So that is the reason.
Okay, thank you again, gentlemen, for brilliantly illustrating the value of satellite imagery and analytics, that value that it can be provided for vegetation management. And so as our next speaker joins the stage, I want to again invite the audience to answer a poll in the polls tab. Have you used high-resolution satellite imagery in your projects before? Let us know in the polls. Joining us now on the stage is Nathan Mercer, VShape expert and software engineer at Intermap. Nathan holds a bachelor's degree in geomatics engineering from the University of Calgary and holds professional engineering status with APEGA. He has been with Intermap Technologies for 20 years, developing and supporting IFSAR production, editing software, and creating products around digital elevation models. Nathan is the developer of the Up42 ViewShed algorithm and the upcoming RFViewshed processing block. We're happy to have you here, Nathan, and the stage is all yours.
Thank you very much, Elizabeth, and thank you everyone for for being here. This is exciting. I'm going to be presenting for you understanding the versatility of viewsheds for line of sight analysis. So one of the first questions, of course, some people might be asking is, what is a viewshed? So a viewshed is a map. It shows the area within a radius of a given location. You can call that location your observer or transmitter. So an area that is visible from that observer. So when we say visible, we mean in terms of direct line of sight. So if you look at that example image on the left here, you can imagine your observer or your transmitter, if you want to call it, at the center of that image, of that circle, I mean, and the viewshed is the red and green colors there. So the green represents locations within that radius that are visible from the observer. The red are locations that are somehow obstructed. It could be from the terrain, from a building, from something else, but they're obstructed and they can't be seen from the observer. Besides the standard viewsheds, there's also RF viewsheds, which you can see on the right. RF standing for radio frequency, and they show something similar, but rather than just the binary on or off, visible, invisible, what you see is a range of colors where the colors represent the amount of signal that you're getting there. So there's some signal drop off. Your example again, image on the right, your observer is somewhere near that little red patch there, and of course red is the highest signal strength, whereas out on the blue is your low signal strength. The loss of signal is calculated from various factors such as the distance, the antenna gain, the oxygen loss, expected amount of rain, and other factors like that. So, what are some of the use cases? Viewsheds are used in various different infrastructure and utility planning. We'll be going over telecommunications, renewable energy, construction, and drone UAV planning. So let's go into those in detail, starting with telecommunications. So viewsheds are commonly used in telecommunications industry for tower site selection and determining network coverage. It gives you the direct line of sight from one tower to the next. And as shown in the image on the left, you can actually use multiple viewsheds together to evaluate tower coverage over a large area. An RF viewshed is useful in telecommunications because you're of course interested in the signal strength as well, and so you can get the signal strength within the range of the tower, taking into account the frequency, the orientation, rain rate, oxygen loss, as I mentioned, all those various factors. And one of the other use cases is renewable energy and construction. So when you're talking about these industries, viewshed analysis is important for the planning process, and they can be combined with other types of analyses to decide on the feasibility of the project. In both cases, the viewshed is used in what is called a visibility impact analysis, which determines the change to the visual qualities of the landscape, positive or negative, due to the change in visible elements within that landscape. So, for example, if you think about renewable energy, you may want to plan a wind farm or a solar farm. In both these cases, it might be the case that it is a negative visual impact because there are people who believe that solar and wind farms are an eyesore and they don't want to be able to see them. It could be a situation where it is a positive impact as well. There are people who may want to be able to see those because it makes them feel good about doing something positive for the environment. And when you think about construction, when choosing a site to build a large feature, for example, visibility impact analysis might show that the new feature would obstruct visibility of an important landmark from certain locations. And there might be people who actually paid extra for those locations because of the ability to see that landmark. So you'd have a negative impact there for those people. You could potentially have some positive impact with construction as well if there's something that maybe you're building a new landmark or building advertising or something that you want to have the most visibility possible. In that case, you use the ViewShed for positive visibility analysis. When it comes to drone or UAV planning, ViewSheds can help avoid sending out ground crews to check on site conditions, and that can be done in the office beforehand. ViewShed can help plan where to stand and at what height to fly your drone to maintain a line of sight throughout the given corridor. There might be legal or even technical reasons for maintaining that line of sight. So if you look at the example images on the bottom there, there in each case that you have a blue line which represents where you plan to fly your drone, and on the left, if you fly at 25-meter height above the ground, you're obviously not going to have much visibility and you're going to be completely obstructed. You move higher up to the 50 meters and it's getting better, but once you get to 100 meters, you have your full visibility. So that's how it helps drone and UAV flying. And now I'm going to speak about the data behind ViewShed analysis. So in order to create a ViewShed, elevation data is required that in order to identify the terrain and or obstacles blocking your line of sight. There's two main types of elevation models that we talk about. There's the DSM. The DSM is digital surface model. It contains surface features such as trees, buildings, and other man-made objects. And then there's the digital terrain model, which is with the surface features removed. It's a bare earth model. The ViewShed processing block in Up42 is what we call DEM agnostic. So it can be run on whatever DEM you provide it. A DTM, DSM, that includes intermaps DEMs that are streaming through Up42 as a data block, or any other data block that is available in Up42. You could even if you want to use your own data, you can make that as a data block in Up42 and use that as well. It's also important to note that the resolution and the accuracy of the ViewShed is directly related to the resolution and accuracy of your elevation model. So the higher the resolution of the DEM, the higher resolution of your ViewShed. And that's explained here, or well, in your images below, what you're seeing is DSM versus DTM. On the left, it was with the DSM, and as you can see, there are a lot more obstructions. That those buildings, behind those buildings is all red, whereas on the right, since it's a terrain model, those buildings are not in it, and it's quite visible in there. So what do you need to use? What's better, a DSM or a DTM? So in most cases, a DSM is what you're gonna want, because it has those obstructions, and that's kind of what you're looking for, right? You want to see, can I see through where's the buildings, trees, etc. are going to block. So in most of mainly all those use cases we saw earlier, a DSM would be most likely, like the telecom network planning. However, DTM could be useful, maybe for wind farm planning. Wind goes through obstacles and around them. So maybe it's not important to know about those. Or potentially if you're in some rural area, you don't really care too much if it's all vegetation, and you know that the vegetation can be removed to accomplish your line of sight. So let's go through the processing block on Up42. So what you're seeing here is, of course, the Up42 console. Most people would be actually accessing through the SDK or API, as we saw earlier. However, this shows what you need. You need your AOI, and your AOI, it's important to make sure your AOI, whether it be a bounding box, polygon, or whatever, it must cover the entire coverage of your ViewShed. And when you pass in the parameters, the parameters you see on here are the same that you'd pass through the API, the SDK. You just pass in your location of your observer, aka transmitter, and you can pass in a height of that transmitter. You can also pass in the height of the target that will be within the field of range, and a maximum distance. So that's your radius around your observer. And you can also pass in a start azimuth and azimuth degrees, which basically focuses or directional, makes your viewshed more directional. You get a pie shape out of that rather than your full radius. And your results come back, and what you get back is actually a GeoTIFF file with transparency. So you'll be able to overlay that on top of, say, DEM or imagery or something, whatever you want, in order to view it in whatever viewer you're comfortable with loading a GeoTIFF file in. You also can get bad statistics. For example, in this, it's important to note, this will come up in the next slide as well, but the processing time for this run that I did here with NextMap 1, so 1 meter data, took 4 minutes 27 seconds. As you can see down below, half of that was actually for streaming the data and half for the viewshed. So you can get those statistics here as well. So now your processing time, it depends on various factors. So your resolution of your DEM, like I said, I used a 1 meter DEM here. Your size of your AOI, your radius that you choose, and the streaming or versus downloaded data. Are you streaming your data, downloading? And of course, that's the streaming part that you'll see, the data download time. So what effects does DEM resolution have on your viewshed? So there are a couple effects, and of course, as mentioned earlier, the resolution is directly related to the resolution of your viewshed. So in your example images below, on the left is using NextMap 1, on the right is using NextMap 10. You can see the pixelation in the NextMap 10 one because, of course, low resolution. In some cases, that's all you need, right? You don't necessarily need quite the high resolution, so that might be useful. But the reason it might be useful and you might want to go that way is because of the processing time. Now, I mentioned last slide it took 4 minutes 27 seconds. I ran the exact same area here with the NextMap 10 and it took 42 seconds. So there is a significant impact in processing time. So you can use the lower resolution DEM for preliminary work when you need quick results. And then when you need a final design work, you can use the high resolution DEM. And as mentioned before, there is RFViewshed. Now, there is no RFViewshed analytic or processing block quite yet, but it is on its way and it should be coming soon. So stay tuned for that. I'm not really going to go through much else here, just that it is on its way, and there will be, of course, more parameters to input, but we'll stay tuned for that. So what have we seen in this presentation? We've seen how visibility impact studies are an important part of infrastructure planning, and they can cut costs. They can cut significant time and cost for crews by enabling visibility studies to be conducted in the office rather than sending out a crew to do a site survey. And if you want to take a closer look, there's the link below to the intermap processing viewshed processing block in the Up42 marketplace. Of course, you can do the search from the marketplace on viewshed, and you'll find it quickly as well. So I'm open for any questions now.
Thank you so much, Nathan. Really insightful presentation. We had some questions pouring in, and actually, I think this one might be relevant to the second to the last slide that you were showing about maybe the difference in using different resolutions. So this person wants to know, do the outputs from these surveys, from these results, qualify as legal survey quality? So can it be used for things like compliance?
I'm not sure the situation where you need that, but if you do, it's all dependent on, and you were exactly right, Elizabeth. It is related, your resolution of your DEM and your versus your viewshed, and it all comes down to how accurate is your DEM for those legal requirements. If those legal requirements need specific accuracy in terms of your elevation, right? You need your building heights to the millimeter. Then your underlying DEM is going to be needed to be accurate to that millimeter, right? So it really does depend on your underlying DEM that you're using.
We have another question, and maybe this also ties into the algorithm that's coming to the Up42 platform. Do you offer also like more advanced algorithms beyond line of sight? So maybe things like ray tracing, this person used as an example of any frequency. Is that what we can see with the RF algorithm that's coming to Up42?
Yeah, so the RF algorithm, as mentioned, it is more advanced. The basic ViewShed is straight line of sight from the top of the transmitter to the top of the receiver. Whereas the RFViewshed takes into account, as I mentioned earlier, signal loss from various factors, and including in there was oxygen loss, rain rate, etc. So that's what we're taking into account there. So the RFViewshed is definitely a more advanced algorithm.
Do you guys also offer optimized distribution algorithms with Intermap? Rather than just the surrounding area, but actually maybe where the distribution should actually occur?
I'm not sure I understand the question. So where the distribution can occur? I'm sorry, I don't really understand that question.
So essentially, I think what Leonard is trying to ask is for optimized distribution, where should you essentially place certain towers in order to ensure the maximum reach? I think that's essentially what he means.
Oh, okay. So it's almost like a reverse.
Exactly, reverse engineering. Yeah.
Yes. No, that's not something that you can do at the moment with this processing block. So that is interesting though, and it's something that we can potentially look into.
Okay, great. Thank you so much, Nathan. Really had some great questions come in from the audience, and again, just such a truly insightful presentation. There were some more questions that came in that we'll maybe hold for our group discussion, our panel discussion at the end if there's time. But on that note, and as our final speakers join the stage, I invite you all again to check out the poll tab for our next question coming in. So would you actually be interested in leveraging ViewShed analytics for your businesses? And if so, what area do you see the most value in? Feel free to answer in the polls. Now we have our final two speakers joining us on the stage, Sarah Thompson and Sean Malamed. Sarah Thompson is a customer success technician at Catalyst with 6 years of experience supporting customers around the world, from government agencies to private industry. She assists customers in developing and automating remote sensing workflows to help them achieve their goals. And joining Sarah is Sean Malamed. Sean is a product marketing manager at Catalyst and has over 15 years of combined education and professional experience developing and implementing remote sensing tech for private, public, and defense applications. Sean specializes in geometric and radiometric correction of optical satellite imagery, as well as automating insight extraction through machine learning and AI. So with that, the stage is all yours, you two.
Wonderful, thank you so much. So as Lizzie mentioned, we're going to be showcasing how we can monitor ground displacement for very vast areas of infrastructure coverage, often ranging in thousands and thousands of kilometers of overall infrastructure. So we're going to start off by just quickly providing an overview about who we are, Catalyst, and this new brand that we've launched. So Catalyst is a PCI geomatics brand that was launched back in October, and our main goal is to bring Earth observation science and data and information and insights and make it available to more people, make it available to more end users, to decision makers, in order to help create a more sustainable and manageable planet. The problem we're here today to discuss is how critical infrastructure is consistently at risk of damage, downtime, and failure, and this is due to the stresses that are caused by uneven ground movement in and around those infrastructure components, whether they're pipelines, whether they're roadways, bridges, and so on and so forth. One of the challenges around this is that today's monitoring programs for critical infrastructure, they're full of data gaps. So, and this is really due to limitations in costs with the current terrestrial surveying techniques that are employed today. So we have two main examples that are the most common used for surveying techniques using terrestrial formats. And this one is, the first one is the fixed GPS GNSS stations. So these are located in a very fixed location, capturing data in real time. And then we have manual surveying, which are deployed to get a variety of measurements over different positions. So we're going to discuss some of the challenges around those, and then how our INSAR capabilities can help supplement this. So if we look first at fixed GPS GNSS locations, one of the benefits, as I already mentioned, is that they provide real-time information, often down to the second or millisecond, around ground movement. So they provide very little data gaps in terms of the temporal, the data that it's collecting. The problem is that they're very expensive to install, so oftentimes they're very sparsely located. So you have these large spatial data gaps where we really have no information that's being captured in between them. So we often have to interpolate and make some decisions around where we are capturing this information. This is often supplemented and complemented by using manual surveying. So then, in order to fill in some of these no data gaps, they'll send crews out, but the problem with this is that it's very expensive, it's very time consuming. So they're often, while they can help fill in some of those spatial no data gaps, they're often still left with spatial no data gaps, but also in terms of the revisit time or how often they can update the measurements, that's often left to weeks or months, and depending on the budget, depending on the project at hand here. The other challenge with this is that there's safety implications. A lot of times these crews need to get special safety certifications because they're often working in very remote, and a lot of times the areas that we care to get displacement measurements around are on dangerous slopes and curbsides. So it's a very, we're also putting surveyors at risk in this case. So what we're suggesting here is that we can supplement, we can complement these activities and often reduce the reliance on those terrestrial surveying activities by using Spaceborne Radar or INSAR technology in order to capture much more dense network of points over large areas that are updated on a more frequent time schedule. And what do we offer in terms of catalyst displacement mapping? So we're using what's known, and this is the only science I'm going to really go into it at this point, is what's known as short baseline subset persistent scatter interferometry. That's a bit of a mouthful. But it's basically a hybrid approach to ensure that we're getting highly reliable measurement points for what's known as stable targets. And this is great for infrastructure monitoring. And what we allow you to do is to build your own workflows to measure ground displacement. And this is the important part, is we can achieve millimeter level accuracy with this technique with a high density of reliable, so I want to underline that point, measurements that are updated regularly. And this, just to show you an example, if we look on the left side, you can see that we can really get a coverage over a large area to cover vast networks of various infrastructure, whether it's highways, pipelines, subways that you want to monitor that are underground. So there's a variety of aspects that we can cover, and we can capture very, very large areas. But what's also nice is we can build this information because we're getting regular updates as depending on what satellites we're using. We can build this into complex monitoring programs that can provide alerts when potentially infrastructure is at risk. Now, one of the main benefits around this is that we can, as I mentioned, we can cover very vast areas, and we can, and in this example here, we're using a Sentinel-1 image, which is a free data source. It's capable of covering up to 42,000 plus kilometers squared. It's got a 12-day revisit time, 10-meter resolution. So the resolution in this case is a little bit more coarse, but it's great for getting a general sense, and for certain types of infrastructure monitoring projects can be very valuable. Once again, the big benefit about these are that we can really get these large areas, high density, regular intervals, and it's very cost effective, especially when compared to using traditional or terrestrial surveying techniques. But if you require higher density information or more detailed information, we can also use commercial data. So here we did an example, and we actually just took an insert from the Apple headquarters in the San Jose area, and we used Terrasar X imagery, which is commercial data. The coverage varies depending on your area of interest, They can get up to, I believe, 4-day revisit time and up to 25 centimeter resolution. In this example, we were using 1 meter resolution data. And as you can see, we can get very dense networks of points covering the area of interest. So some of the general benefits of why would you want to use this information for displacement mapping around key infrastructure? Well, it can improve the quality. So one is that we can get historical data. There's a lot of INSAR data that dates back to the mid-90s where we can actually tap into that information to get an historical understanding of how the ground movement is occurring under potentially future sites that you can build into your structural or geotechnical engineering models and projects. We can reduce the risk by filling in those spatial gaps. So we're not really suggesting that this is a replacement for terrestrial surveying, but it's a great complement to terrestrial surveying that can also reduce your OpEx costs because you can minimize your investment in terrestrial surveying because you're now capturing a new source of ground measurement data. And really your terrestrial surveying can now be more used as a validation source as opposed to as the primary data source. So what do we offer on the processing blocks? Well, we have today already our ground displacement, which uses actually a DINSAR, so differential INSAR technique. And this is really ideal for generating general trends and overviews and at about a centimeter level precision. So it's good for, it's still a very valuable data source for a variety of types of projects, but it also complements what's coming soon. And we have our new ground displacement SBAS PSI technology that is going to be coming soon as a processing block. And this is what we're going to showcase in a moment. And this is ideal for reliable infrastructure monitoring at that very precise millimeter level precision where we can get very high density, reliable measurement points. So with that, Sarah is now going to show us a live demonstration of a use case for this and how we can work with the processing block, where we can show using the data block, connecting it to our processing blocks, and then ultimately building a data stream into a third-party application or a third-party solution within your own organization. So with that, I'll let you take it away, Sarah.
Sure. I'm just going to share here. There we go. And so as Sean mentioned, we currently have the deformation mapping processing block on Up42, and we'll soon be adding the new persistent scatters interferometry, or the PSI, processing block. So these processing blocks can be run programmatically and as such can be integrated into existing workflows. This allows you to quickly process SAR data on demand over your area of interest. So the outputs from this workflow can then be downloaded, displayed, and added to external applications. I'm going to first show an example web application which we have developed using data derived from the workflow on Up42, Catalyst Insights. So with this application, we can view displacement maps and identify areas of subsidence and uplift, which can be damaging to our infrastructure. So here we see the area of interest, Bakersfield, California. This is a particularly interesting area for INSAR processing, as we know that there is ground deformation that occurs. So groundwater is extracted for irrigation of the agricultural fields in this area, and as such, subsidence occurs in the nearby urban areas, and this subsidence can be detrimental to infrastructure. So with this application, we're monitoring a specific power station. So you can see that with the alert here. We will then get a warning if the subsidence near the power station is above a set threshold. So I have overlaid the electrical transmission lines, which is the infrastructure grid being monitored in this application. And I've also turned on the cumulative displacement layer, which is generated by the same INSAR ground deformation workflow as available on Up42. So the results in this application were derived from a large stack of images, so we can see the trend over time as I start the time series. So when looking at the time series, we can see that there's different levels of subsidence throughout the year, depending on the amount of water that's extracted from the aquifer. You will see that the area near the alert is an area of higher subsidence. So if we zoom into that alert location, we can view the results from the persistent scatters interferometry processing block, which will soon be available. So you can see here that we get points at this point. And so the PSI technique processes a stack of SAR images to identify stable points, and ground deformation is then calculated for each of the points. As these points are known to be stable, the deformation measurements for the points are highly reliable. So we can be confident that these points are within a few millimeters of accuracy. So as we continue to zoom in on our area of interest, we can see that our alert location is a power station. We can then select all of the points around this power station. And we can look at a chart showing the cumulative deformation values for each point. So from this chart, we can see that we have an uneven deformation around the power station. This can lead to damage to the infrastructure system. So with this information, we can then determine if we want to send a ground crew to check the power station infrastructure in this location. So this application is just one example of how the deformation mapping processing block could be integrated so data can be constantly processed in order to perform analysis and real-time monitoring. There are many more potential applications like web GIS services, depending on a user's requirements. In this particular case, Sentinel-1 imagery was used, but we do support many SAR sensors, including high-resolution sensors such as TerraSAR-X. So using this higher resolution data, we'll generate a denser network of points, which can then be used to monitor smaller infrastructures such as pipelines. So now that we've seen how the data can be used in a real-world application, I'll show an example of how to run the Catalyst displacement mapping processing block that's currently hosted on Up42. So for the purposes of this demo, we'll be running this in a Jupyter notebook so we can see the code and view the results. So this script processes Sentinel-1 images over a subset of that same area of interest that we just looked at in Catalyst Insights. So the first step in the script is to import the Up42 library in order to access the displacement mapping processing block. The next step will be to authenticate the workflow with Up42 and access the Sentinel-1 images, define the AOI. So in this section, we are getting two tasks. So this is the task in order to get the Sentinel-1 images, and this is the task to access our processing block. So we also set our coordinates here for our area of interest and the three Sentinel-1 images that we'll be using. So then we will quickly run a test to confirm that the data is available and the jobs are configured properly. This allows you to confirm that everything is set correctly before running the full workflow. So from there, we can then run the full workflow. And this is the full displacement INSAR workflow. So at this point, the Sentinel-1 scenes are processed through each step in the workflow from data ingestion, co-registration, phase unwrapping, and deformation calculation. So once the process is complete, the results can then be downloaded from Up42. In our notebook, we will then proceed to display the results. So we used open source code for this section to open and display the data. So this output is a cumulative displacement in millimeters that has occurred over the 1 month time period between our three images. So we can see that there is a greater displacement in these two sections, which are urban centers, and the central area of the agricultural field, which includes much less displacement, closer to 10 to 20 millimeters. So we can also view the coherence raster, and this coherence layer can be used for quality assurance purposes. The values in the coherence raster correspond to the confidence in the measurements for each pixel. So in the areas of high coherence, which is the white, we can have more confidence in the result. Whereas areas of low coherence, which is the darker areas, we have less certainty in the result accuracy. So as we can see here, there are a number of areas of lower coherence. This ties back to the benefit of the PSI workflow. So in that workflow, each persistent scatter point that is collected is a stable point, and we have high confidence in the results from each point. So this results in a collection of points that show high confidence displacement values. And so here we've shown an example of our existing displacement mapping processing block and viewed the overall trends of subsidence and uplift across our area of interest. So the soon to be available persistent scatters interferometry processing block will allow us to generate highly accurate deformation measurements. With both processing blocks, the INSAR results can be used to perform real-time infrastructure monitoring over large areas with less expense than manual surveying and fixed GPS stations. So at this point, we are open to questions.
Sarah and Sean, really insightful presentation. I liked seeing also the contrast between the PSI algorithm and the DNSAR. I guess one thing to clarify here, you mentioned where both of these algorithms have their benefits as compared to ground measurements, in situ measurements. But are there differences in like the costs and benefits of each? I noticed in the PSI method, a lot of those points were located on things like buildings. So maybe, are there different areas, like maybe PSI works better in more urban environments or something like that? Insights that you could give us?
Yeah, absolutely. So PSI tends to work a lot better in urban and on stable features, because that's actually one of the main things we're looking for, are stable features. So we actually look through a stack of SAR imagery to identify where the amplitude is very consistent. So that's how we identify that it's a stable feature that's not going to be moving. So it works really well on infrastructure like pipelines, on roadways, on buildings, on built-up area, and also low-lying areas where there's not much vegetation. The areas where you would need things like corner reflectors to help find stable or create stable points, artificial stable points, would be things like forested or very dense canopies, where that's where it's going to have some challenges. But we do have also techniques in order to help mitigate some of those, and we use some interpolation techniques where we do find stable points even within the canopies. We can help interpolate around that where we can't get a lot of stable points. And that's also why we use a hybrid short baseline subset approach, or the SBAS approach. That actually helps create, it gives us more data, so that when we are finding stable points, we just have more information to work with, and therefore we have a higher probability of finding a stable target.
We have another question about the atmospheric effects, and even a question about how clouds impact analysis. Maybe you could give some insight on that as well, for both the PSI and for the DNSAR.
Sarah, if you want to take this away, by all means, I'm happy to answer it too, so it's your call.
Sure.
Go ahead.
So we do have corrections for atmospheric effects. It's part of one of the algorithms that's part of the full workflow, does take that into account. The benefit of using SAR data over other types of satellite imageries like optical data is that there is less effects from cloud. And so that can help, that helps people be able to get data from a larger period of time. And so you're not trying to, find those images that don't have clouds, because that's just less of a problem.
One more question. We have an audience member that wants to know, is the displacement relative to the line of sight or the absolute elevation?
So once again, Sarah, it's all yours if you want it. I'm happy to answer it too.
So the displacement is relative to the, I think, line of sight of the sensor.
It is line of sight, yeah. Yeah, so we're line of sight right now. We are working on providing a vertical displacement as well. And actually, Lizzie, I think you provided me some pretty cool code as well in MATLAB. So
Yes.
I'm sure there's ways that you can also get those information and also build that line of sight. The vertical displacement yourself. But that is something that we are currently working on, and we expect to be available soon.
Yes, absolutely. So I think with that, that's all the time that we have for the individual questions. So thank you again, Sarah and Sean. Before we actually move over to the roundtable section, the panel discussion, we'd like to get an idea about what you as the audience members would like to see in our next webinar series. So check out the polls tab and give us your thoughts on what you think would be a valuable next topic for you and for your business. So at this point, I invite our speakers to the stage. Feel free to join us here as our audience members answer the polls. So we just have a time for a few questions. We'll try and incorporate some of the questions in the questions tab that we didn't get a chance to answer during the presentations. But let's start, let's kick this off, this panel discussion, with a couple just general questions for each of you, or at least maybe one person from each presentation. So what are the biggest challenges that you see in infrastructure management as it relates to geospatial tech today? Maybe we can start off with AI Dash and then make our way around the same order as the presentation.
Nathan, you want to take this one?
Yeah. So basically, the infrastructure management, you require the latest availability of the data as well as the quality of the data. So obviously, if you want, sometimes it happens that the latest data is not available, then we have to basically go off for tasking and all. So that is the biggest challenge which we face during the infrastructure management. And we have to basically then plan accordingly.
And Nathan, what are your thoughts?
Very, very similar, actually, and it comes down to data again, and the quality of the data, but also the consistency of the quality, because you do get very good quality data in some locations, whereas in other locations it may be much lower quality. So it's difficult to find very consistent over large areas that you need to the quality that you want. So I think that is a limitation as well.
Yeah, absolutely. And Sarah or Sean, do you have some input there too?
Sure. So similar to what the two other guys were saying is, the data, right? We need to have, and especially for INSAR, you need to have a fairly large stack of data over a diverse time period to be able to get results that are meaningful. And so, the benefit is that there are sensors such as Sentinel-1, which are freely available. And so it's easier to get that sort of data. But then if you're looking at more, smaller infrastructure, can you get that high resolution data in the quantity necessary with, the correct pairs that work well for INSAR processing? And so, it's a possible limitation, although, certainly from our side, we've been able to get some great results.
Yeah, absolutely. And I guess that's also where, things like tasking come into play. If you're able to plan in advance, definitely something to take advantage of that I don't see as, taken advantage of as much as maybe I would like to see in the geospatial tech industry. Another thing is maybe, seeing how different companies like Up42 are aggregating all of these different data sets, so you're essentially increasing the likelihood of the revisit for some of these things. But yeah, absolutely, lots of ground to make, lots of room for improvement in that regard. So I think we can move on to the next question. Do you all think, in your opinion, that remote sensing technologies will, as we make these advancements, will replace traditional manual or in situ monitoring solutions? What are your thoughts, AI Dash?
Yeah, of course. So we have started with this vegetation management use case, getting into other use cases. Whatever results we are seeing, I mean, if people can do this at scale for very large areas, so why would you want to do it manually or through other mechanisms? So yeah, we are banking heavily on remote sensing. Yeah.
Yeah, I bet, Rahul. Nathan, do you also want to chime in?
I agree. I believe absolutely yes. As the data improves and we get it more available, then we're on that path for sure. There may always be some niche areas where it doesn't completely replace it, but I think in the general sense, yes.
Yeah, I definitely agree.
Also, go ahead, Sarah.
Sorry, go ahead.
So basically,
Go, Sean.
That's bound to happen in a webinar. Here, maybe Sean, you take this one. I'll delegate it.
Sure. No, I think, we're all in the geospatial space in order to, because we believe strongly in our technology, and we believe that this is going to be a strong replacement for doing in situ and ground-based surveying. Even just looking at the displacement mapping capabilities that we've seen, I think once the idea of like having to send a crew out there where they're liable to safety concerns, you know, if we can mitigate that, and we can also capture very large areas and get the dense point measurements, as well as getting them updated to the point where we're going to be getting same-day measurement, same-day revisits. So I think it's just a matter of time, and there's a lot of evangelism that has to happen. People need to get comfortable, like, where are these measurements coming from? It seems like magic to some people, so we need to definitely do a lot of work to you know, showcase that this is real science and these measurements are valid.
Yeah, absolutely. This same day revisit, you know, just a couple years ago seemed like a pipe dream, and now we see these companies launching all of these satellites in tandem, and it's really exciting to see. I totally agree. I think we'll have some time for some of these questions. I'm not sure if I'm going to be able to cover everybody, but some of these questions that didn't get to be answered during the presentation. So let's start with, again, a question for AI Dash. How are trees with higher failure potential detected? Maybe another person had asked, I saw about maybe the infrared band or the near infrared band, how that is used. And yeah, would really appreciate your insight on that.
Sure, Nitin, you want to take this one?
Yeah, sure. So basically, there are multiple ways we basically detect higher failure potential. So one is basically if the tree is how much a tree is basically distance from the wire in terms of vertical as well as the horizontal clearances, and then basically we also detect the health of a vegetation through time using as well as near infrared or red edge band as well. Yeah. So that gives the indication of the health of the vegetation.
Yeah, absolutely. This one, actually, Sean, we were just touching on this, and it was upvoted quite a bit. So with these new providers, with this more rapid revisit that we're seeing, what are maybe some things, some opportunities for critical infrastructure monitoring that will be made available through these more rapid revisits?
Yeah, I think you're going to start to see real-time monitoring or near real-time monitoring programs that are going to be implemented with direct alerts and actionable information about what to do about those. So it's not just going to tell you that something's wrong, but you're going to start to get more insights about what's potentially wrong and even some indications about what you should do. So you're going to start to see a lot of, we kind of coined it prescribed maintenance activities as opposed to preventative, where it's going to be a lot more situational and making sure that it's going to reduce costs from the operations perspective, as well as ensure that you know, there's no loss of downtime and services remain up.
And actually, Sarah, another question related to these displacement algorithms. Is there a minimal and maximum surface value that you can detect in these algorithms? And how does that depend on the data that you use?
So I think what they mean by, so the surface value is the amount of deformation that is detected. And so it depends on the data that is being used and the resolution of that data. And so, you know, lower resolution, such as Sentinel-1, you're going to have, you know, you can't necessarily detect to the same accuracy, whereas higher resolution, you would be able to. Also with, you know, different types of workflows, like the differential INSAR versus the persistent scatterers interferometry. So with the PSI, you can get that higher accuracy within, you know, a few millimeters of change that you can detect.
Yeah, and I can actually help with that too. We recently did a validation study over San Jose with TerraSAR-X data where we compared it to third-party GNSS station data, and we were able to consistently get it within about 5 millimeters of the GNSS data. And also keep in mind that there's also potential error of the GNSS data, so it could even be better than that. But yeah, 5 millimeters, within 5 millimeters is what we were able to get, and that study is going to be released shortly.
Great, that's great to hear. So I think with that, that's all the time we have for our webinar. And thank you all for joining us today, and many thanks to our speakers for their insightful presentations and their thoughtful answers to all of our questions, both, of course, at this roundtable, but also throughout the presentation. Keep in mind that the data and algorithms shown here today are available on the Up42 marketplace, so stay tuned as the infrastructure monitoring and management solutions on Up42 continue to expand. If you haven't already familiarized yourself with the Up42 platform, we have an intuitive user interface where you can click together all types of geospatial data with off-the-shelf algorithms and a workflow and get immediate insights. You can claim your complimentary 10,000 Up42 credits on our platform by clicking the button on your screen. Those credits can be used for any open source data, all types of vegetation indices like we discussed today on Sentinel-2, and much more, even beyond just infrastructure and vegetation management use cases. As you can see, we'll have a slide where you can see all the different data types of high resolution data that you can access with Up42 and off-the-shelf algorithms, and even create bespoke solutions with Up42 using our Python SDK. For more on this, just contact our sales team. If you have further questions that we didn't get around to answering today, don't worry. Our team at Up42 will be in touch, and you can feel free to ask your questions then. Again, thank you all so much for coming, and for more ideas on how to upgrade your infrastructure workflows or just your geospatial insights overall, come visit us at up42.com.